The formation of the Earth is a complex process that has been explained by scientists over many years of research. It begins with the formation of our solar system about 4.6 billion years ago. In the first stage, the Sun and the planets around it formed when a large molecular cloud collapsed. This molecular cloud was made of dust and gases, and during the collapse it was pulled towards the center to form the Sun. In the outer parts of the collapsing cloud, a rotating disc-shaped structure formed. The dust and gas particles inside this structure collided and merged over time to form larger structures, the planetesimals. As these planetesimals grew and merged, planets like Earth were formed. In the early stages of Earth's formation, it was very hot due to the energy generated by the collisions of planetesimals. This heat caused the heavy elements inside the planet, such as iron and nickel, to gather in the center and form the core. This process also led to the formation of the layers of the planet: core, mantle, crust. The Earth's surface was initially completely molten, but over time it cooled and became a solid crust. Volcanic activity, meteorite impacts, and other geological processes led to the continuous reshaping of the surface. These volcanic activities also produced the first components of the atmosphere. After the formation of the atmosphere, when temperatures on Earth's surface dropped low enough, water vapor condensed to form oceans. These oceans provided a favorable environment for the first life forms to emerge. The first life forms probably emerged around hydrothermal vents deep in the oceans around 3.8 billion years ago. The Earth's magnetic field was created by movements in the planet's core. The magnetic field helped protect life on the planet's surface by deflecting much of the harmful radiation from the Sun. Over billions of years of evolutionary processes, the land masses moved continuously to form the continents we know today. This process, called plate tectonics, caused continents to move, collide, and separate. These geological activities led to the formation of mountains, valleys, and other landforms. In conclusion, the formation of the Earth was the result of a complex interplay of various cosmic and geological processes, starting from the formation of our solar system. These processes shaped the Earth into what it is today and contributed to making the planet a habitable place. The Earth's magnetic field is generated by the dynamo effect that occurs in the planet's core. This effect is driven by the movement of molten iron and nickel in the liquid outer core. The Earth's core consists of two parts, the solid inner core and the liquid outer core. Although the inner core has a temperature of about 700 degrees Celsius, it is solid due to extreme pressure. The outer core is liquid at this temperature. The molten metals in the liquid outer core move due to the Earth's rotation and temperature differences. This movement creates electric currents, which in turn create a magnetic field. This process is called geodynamo. According to the geodynamo theory, convection currents in the liquid outer core and the Coriolis force cause these electric currents to produce a regular and continuous magnetic field. The Earth's magnetic field flows from the inside out, creating a protective shield around the planet. This field is concentrated around the magnetic poles, and the magnetic poles are not completely aligned with the geographic poles. The magnetic poles can shift over time, and this phenomenon is called magnetic drift. An important component of the magnetic field is the magnetosphere. The magnetosphere is the region that protects the Earth by deflecting most of the charged particles from the Sun, the solar wind. The outer boundary of the magnetosphere is shaped by the pressure of the solar wind and is usually about 60,000 kilometers from Earth. The solar wind can create geomagnetic storms by compressing and shaping the magnetosphere. Earth's magnetic field not only deflects much of the harmful cosmic radiation, but also protects the upper layers of the atmosphere. This protection maintains the atmospheric conditions necessary for the sustainability of life. The presence of a magnetic field enables the operation of compasses, which are capable of magnetic direction finding on the Earth's surface. This feature has played an important role in navigation and exploration throughout history. As a result, the Earth's magnetic field is generated thanks to the dynamo effect in the liquid outer core and acts as a protective shield around the planet. The magnetic field protects the Earth from harmful particles from the Sun and contributes to the sustainability of life. The displacement of landmasses is explained by the theory of plate tectonics. According to this theory, the Earth's outer crust, the lithosphere, is made up of large and small plates that interact with each other. The lithosphere plates move over the softer and partially molten asthenosphere. This movement is driven by convection currents, which are the result of hot material in the mantle rising and sinking as it cools. There are three main types of plate motion: divergent, convergent, and transform. Divergent motion occurs where the plates move away from each other. A typical example of this type of movement is seen on mid-ocean ridges. At these ridges, mantle material rises to the surface and forms new oceanic crust. The new crust is pushed sideways over time, a process known as ocean expansion. Collisional motion occurs where plates move towards each other. This movement results in one plate diving under the other, a process called subduction or subduction. In subduction zones, deep ocean trenches and volcanic arcs form. For example, the Aleutian Islands, formed where the Pacific Plate dives under the North American Plate, are the result of this type of movement. Lateral strike-slip movement occurs where plates slide parallel to each other. This movement occurs along major fault lines. The most famous example is the San Andreas Fault. Along this fault line, the Pacific Plate and the North American Plate slide laterally, and this movement can cause large earthquakes. Plate tectonic movements cause important geological events not only at plate boundaries but also in the interior of the plates. Plate movement leads to mountain building orogenesis, volcanism, and earthquakes. For example, the Himalayan mountains were formed when the Indian Plate collided with the Eurasian Plate. This collision caused a major uplift and curvature of the plate boundary, creating the highest mountain range in the world. The time scale of plate movements is measured in millions of years, and these processes occur very slowly. However, over time, these movements have shifted continents and shifted land masses to their present positions. For example, about 200 million years ago, the supercontinent called Pangaea was a single landmass. Due to plate movements, Pangaea broke apart and today's continents formed. As a result, the displacement of land masses is explained by the theory of plate tectonics, a process that occurs as a result of the movement of lithospheric plates on the mantle. These movements are the main cause of major geographical and geological changes on the Earth's surface. The process of glaciation on Earth is a combination of long-term climate changes and specific geographical conditions. Glaciation is characterized by the covering of large areas of land and seas with thick ice sheets. This process begins and progresses during periods of cooling in the Earth's climate. The basis of glaciation is the accumulation of snowfall and the accumulation of this snow without melting. In cold climates, especially at high latitudes and high altitudes, snow that falls in winter does not melt completely in summer. Over time, this snow accumulation compresses and recrystallizes into ice. In this process, snowflakes are compressed to form a denser and more permanent ice mass. Glaciation is usually caused by the interaction of four main factors: climate changes, tectonic movements, ocean currents, and orbital changes. Climate changes can be triggered by factors such as changes in the concentration of greenhouse gases in the atmosphere, volcanic activity, and cycles of solar activity. These changes can lead to long periods of cooling, which can initiate glaciation. Tectonic movements also affect glaciation. Shifting continents, rising mountains, and shifting ocean currents can have major impacts on climate. For example, the rise of the Himalayas has caused climate changes in the interior of Asia and triggered glaciation in these regions. Ocean currents regulate global climate by transporting warm and cold water masses. Changes in currents can cause temperatures to drop and ice sheets to form in certain regions. In particular, currents in the North Atlantic can directly affect the climate of Europe and North America. Orbital variations refer to small changes in the Earth's orbit around the Sun. These changes can cause long-term changes in climate by affecting the amount and distribution of energy received from the Sun. These orbital changes, known as Milankovitch cycles, play an important role in the formation of ice ages. During glaciation, ice masses gradually grow and cover large areas. These ice masses move and advance slowly under the influence of gravity. Glaciers erode and transport the rocks beneath them, forming valleys, moraines, and other typical shapes of glaciers. This process drastically changes the landscape and creates a special set of landforms known as glacial geomorphology. The process of glaciation leads to significant changes in the Earth's climate. Glaciers store large amounts of water on land, causing sea levels to fall. In addition, the white surface of glaciers reflects sunlight, increasing the albedo effect, which further reinforces global cooling. In conclusion, the process of glaciation on Earth is the result of the interaction of snow accumulation, climate changes, tectonic movements, ocean currents, and orbital changes. This process covers large areas with ice and profoundly affects both climate and landforms.